General characteristics of ionic compounds. First is physical state. All the ionic compounds exist in solid state. Next is crystal structure. In ionic compounds, ions are arranged in regular pattern in three-dimensional space to form a lattice. And this arrangement depends upon the size and charge of the ions. For example, in case of NaCl, Na positive ions are surrounded by 6 chloride ions and it forms FCC structure, and type of structure depends upon the compound, ionic compound, its size and charge of the ions. Next is high melting and boiling point. Ionic compounds have high melting and boiling point due to strong forces of attraction. Next is solubility. Ionic compounds are soluble in polar solvents like water because they dissociates into ions when dissolved in water. Water is also a polar solvent and it also dissociates into ions. Next is electrical conductivity. Ionic compounds are good conductors of electricity in solution or in molten state, and conductivity is due to the movement of ions in the solution or in molten state. Next is the ionic reactions. Ionic compounds possess ionic reactions. For example, NaCl when reacts with AgNO3, it forms AgCl plus NaNO3, in which Na positive ions displaces Ag positive ions from AgNO3 to form AgCl plus NaNO3. These are some general characteristics of ionic compounds. Next is covalent bond or Lewis-Langmuir concept. It is the bond formed by mutual sharing of electrons between the atoms. For example, in case of water molecules, the hydrogen atoms share their electrons with the oxygen, and here oxygen completes its octet by sharing its 2 electrons with 2 hydrogen atoms, and it forms single bonds with the 2 hydrogen atoms. Next is the example of ammonia, in which nitrogen shares its 5 electrons with the 3 electrons with 3 hydrogen atoms and completes its octet. Here also nitrogen forms single bond with the hydrogen. Next is the example of carbon dioxide, in which carbon shares its 4 electrons with 2 oxygen atoms, forming the double bonds. It means single bond requires 2 electrons, double bond requires 4 electrons, and triple bond requires 6 electrons to form a bond. In case of nitrogen, 2 nitrogen atoms share their 3 electrons to form a triple bond. Next is chlorine atom, in which chlorine contains 7 electrons in the outermost shell, and other chlorine also contains 7 electrons in the outermost shell. They share one electron to complete their octets and form single bond. And all the examples are of covalent bond, in which single bond requires 2 electrons, double bond requires 4 electrons, and triple bond requires 6 electrons. Next is the Lewis structures of molecules. For example, CCl4, in which carbon forms 4 bonds with the chlorine atom, and chlorine atom with lone pair of electrons is shown by dots. This is the structure of Lewis structure of CCl4. Similarly, for COCl2, in which carbon forms double bond with oxygen and single bonds with chlorine atoms, and lone pairs are shown by the dots. And this is the Lewis structure of COCl2. Similarly, for water molecule, in which oxygen forms 2 bonds with hydrogen and 2 lone pairs, and in case of CO3 negative carbonate ion, carbon forms 1 double bond with oxygen and 2 single bond with 2 oxygen, and these 2 oxygen carries a -1 charge, and the whole molecule contains -2 charge. And in a case of SO3, S forms double bond with oxygen, 1 oxygen, and with other 2 oxygen it forms single bonds. and the lone pair of oxygen is shown by the dots. And these are some examples of Lewis structure of molecules. Next is a formal charge on an atom in a molecule. Formal charge of an atom in a molecule or ion is calculated by the formula, which is equal to total number of valence electrons in the free atom minus total number of electrons of lone pairs, that is non-bonding electrons, minus half of total number of shared electrons, that is bonding electrons. Or this can be written as Fc is equal to formal charge is equal to V for valence electrons minus L for lone pair of electrons minus half of S for shared pair of electrons or bonding electrons. Next is the limitations of the octet rule. It could not explain the formation of compounds involving hydrogen, for example H2. Next is the formation of compounds like BeCl2, BF3, AlCl3, etc. All these compounds are electron deficient. It means they contain 6 electrons in their octet or violates the octet rule, although they form compounds. Next is it could not explain the formation of compounds like PCl5, SF6, IF7, H2SO4, etc. All these compounds are electron rich compounds. They contain 10 electrons in their octet, more than the 8 electrons according to octet rule, although they form compounds. Next is formation of compounds of noble gases. Although noble gases are inert in nature, they do not react with other compounds, but some of the compounds of xenon are known. Although they have complete octet, they also form compounds. Next is odd electron bonds or odd electron molecules. It could not explain the formation of odd electron molecules. For example, nitric oxide, in which nitrogen form bond with oxygen, double bond with oxygen and 3 electrons on the bond. Next is nitrogen dioxide. Next is oxygen molecule. Next is sulfur superoxide ion. All these molecules contain odd electrons, although they form compounds and violates the octet rule. Next is the limitations of Lewis-Langmuir concept of covalent bond. It could not explain the formation of covalent bond. It could not explain the shapes of molecules containing covalent bonds. It could not explain the release of energy during the formation of covalent bond, whether the energy is released or absorbed during the formation of covalent bond. It could not explain by the Lewis-Langmuir concept of covalent bond. Next is the VSEPR theory or valence shell electron pair repulsion theory. This theory was given by Sidgwick and Powell in 1940 and was further improved by Nyhall and Gillespie in 1957. According to this theory, the electron pairs surrounding the central atom repel one another and move so far apart from one another that there are no further repulsions between them. As a result, the molecule has minimum energy and maximum stability. Shapes of molecules containing bond pairs and lone pairs. These all shapes of the molecules according to the VSEPR theory. If the number of electron pairs are 2, then the geometry is linear and the bond pair are 2, and the molecule formula of the molecule is AB2. For example, CO2, BeF2, BeCl2, HgCl2. In this molecule, these two electron pairs are far apart from each other and there is minimum repulsion between these two electron pairs, and maximum stability and minimum energy. It acquires minimum energy and maximum stability in this geometry. If there are 3 electron pairs, then the shape is triangular planar and the formula is AB3. Here the number of bond pairs are 3 and the formula is AB3. For example, AlCl3SO3BF3, in which boron forms 3 bonds with the 3 fluorine atoms, which are arranged in a triangular planar shape to acquire maximum stability and minimum repulsions. If there is one electron, 2 bond pairs and 1 lone pair, then the formula is AB2L and the shape is distorted from the triangular planar and it forms to bend shape or V shape due to lone pair bond pair repulsions, and the formula is AB2L. And for example, NO2 SO2O3 SnCl2. Next is when the number of electron pairs are 4 and the shape is tetrahedral shape. The formula is AB4. For example, CH4, SiF4, NH4 positive. All these molecules form the tetrahedral geometry with bond angle of 109 degrees. And electrons are arranged tetrahedrally. Electron pairs are arranged tetrahedrally. If there is one lone pair and 3 bond pair, then the formula is AB3L and its geometry is distorted and it becomes trigonal pyramidal, and there is one lone pair on the 4th atom, one lone pair instead of 4th atom. For example, ammonia NH3, in which 3 hydrogen atoms are bonded with the nitrogen and there is one lone pair on the nitrogen atom. Due to lone pair bond pair repulsion, its bond angle decreases from 109 to 107 degrees and its geometry becomes trigonal pyramidal. Other examples are PCl3, NCl3, NF3, PH3, H3O positive, etc. If the bond pair are 2 and lone pair are also 2, then the formula is AB2L2 and its shape also distorted to become bent shape due to lone pair repulsion, because lone pair repulsions are greater than lone pair bond pair repulsions. For example, water molecule H2S and H2 negative, they form bent shape because they contains oxygen contains in water lone pairs, and lone pair bond pair repulsions are greater than bond pair repulsions. Next is when electron pairs are 5, its geometry is trigonal bipyramidal. It means it contains 5 bond pairs and its formula is AB5. For example, PCl5, PF5, SB, Cl5, AS5, etc., in which 3 bonds are in one plane called equatorial bonds and 2 are in the out of the plane called axial bonds to acquire minimum repulsion. Next is if there are 4 bond pair and 1 lone pair, its formula is AB4L and its geometry is distorted. It becomes seesaw geometry due to lone pair bond pair repulsion. For example, SF4, in which 1 lone pair and 4 bond pairs by the 4 fluorine atoms. Next, when there is 3 bond pair and 2 lone pairs, then the formula is AB3L2 and its shape is T-shaped, in which 2 lone pairs and 3 bonds pairs are shown, and here repulsion is due to lone pair, and its example is ClF3. Next is two bond pair and three lone pair. Its formula is Ab2L3. Here there is three lone pair and two bond pairs. Example is XCF2, I3 negative, Br3 negative, ICl2 negative, etc. And its shape is linear to acquire minimum repulsions. Next is if there are 6 electron pairs, then the geometry is octahedral and its formula is AB6, in which 6 uh, atoms are arranged around the central atom in the octahedral corners. And its example is SF6. If there is 5 bond pair and 1 lone pair, its symmetry is a square pyramidal and its formula is AB5L. For example, ClF5, IF5, BrF5, etc. And due to lone pair bond pair repulsion, its geometry is distorted. If there are 4 bond pairs and 2 lone pairs, it becomes AB4L2 and its symmetry is sphere planar. For example, XCF4, here is also lone pair bond pair repulsion occurs. Next is the calculation of total number of electron pairs, bond pairs and lone pairs. Total number of electron pair around central atom is equal to half of number of valence electrons of the central atom plus number of atoms linked to the central atom by single bond. Next is number of bond pairs or shared pair is equal to number of atoms linked to central atom by single bond. Next is number of lone pairs, which is equal to total number of electrons minus number of shared pair of electrons.